So let's now apply this analysis of the behavior near the singular point to the Bessel function as equation that we are solving here. And once we apply that, we can see the performance for different choices of the integration approaches. And so we have already looked at some plots for the behavior of these solutions. And those plots were obtained by using this behavior near the singular point that we just analyzed. And so in particular here, the ratio of y prime over x takes on a finite value, and that value was used in here for small x. And when x is not small, then of course we can simply evaluate the right hand side as such. And so here we are showing what the error is when we use over this interval of 0 to 2 pi 10, 20 and 40 points using first order Euler method, and then later with the second order Euler method with the same number of points. And so this is the step size that you have when you take 2 pi and divide it into 10 intervals and so on. And the 2 norm of the error that we compute using first order Euler method is found in this way. We start with an error which is like 0.5. Note again that Bessel function starts at value 1 and oscillates, becomes negative with a small value for the extreme negative number that it reaches, and then decays and keeps on oscillating and so on. And so this error is actually quite substantial. It's quite large for a function which is varying essentially from 1 and is decaying to 0. It has an undershoot. It goes to the negative side, as you have seen from plots of the Bessel function. But as we saw for the cosine wave oscillation, when we integrated it using the first order Euler method, is that we have a system of differential equations whose eigenvalues have a strong imaginary part to them, and first order Euler method is not stable for systems that have imaginary eigenvalues. For pure imaginary eigenvalues, this equation, this method, this algorithm would be unstable. And so we're seeing a growth of round-off error when we use this method, and we get large errors as a result. The error itself does in fact decrease as we reduce the step size in an expected way, and that's shared by other norms of the error as well. But we have significant errors, and so if we practically wanted to compute solutions to systems that involve oscillations, we would not use a first order Euler method. We want to use a method which will have intrinsic stability for oscillatory eigenvalues. And so second order Euler is a better method for such problems. Of course, it also works for monotonic problems where eigenvalues are real as well. And so if we contrast the errors, the 2 norm, the 1 norm, and the infinity norm, again we can see that for second order method, as we refine the step size, as we use more steps, error decreases dramatically, essentially quadratically in step size. So a factor here is 2, and error decreases by essentially a factor of 4 every time we halve the step size. Whereas for first order, error decreases in proportion to the step size. Here is quadratic, here is linear. That's why this is called second order, and this is called first order. So with this, we are ready to apply these methods to more complicated problems, more general problems, where we may not have analytic solution, to larger problems, and discover interesting behavior. And so as we do that, I want to add a note of caution that when we compute numerical solutions, it is essential that we ask for assessment of quality of that numerical solution that we are computing, because if we're not careful, as we have seen in some of these very simple examples, we can run into the issue of garbage in, garbage out. That is not of use to anyone. And so if we are careful, we can produce, using numerical methods, solutions to interesting applications, real-life problems that are very, very useful and help solve real-world problems. But we need to be careful.